So the topic here is differentiation. It's kind of standalone. It links to integration, but we'll discuss integration after this one. Obviously, you need to know both. These few pages cover that specific topic. Okay, so that's what we're looking at now, currently. Right, perfect. So you've got the heading, differentiation. What is differentiation? Well, you can just put a note. It's looking at changes, okay, but for graphs specifically, or functions. So you can put a note, differentiation. It's part of the calculus section. So calculus is using algebra practically. Okay, that's what calculus is. Differentiation is, if you wanted to summarize what it is, you can say looking at the rates of change for graphs or functions. Looking at rates of change for graphs / functions. Looking at rates of change for graphs / functions. Okay, second bullet.
Okay.
Second bullet. Okay, what does differentiation cover? It covers derivatives. So the word derivative is what we're looking at when we talk about differentiation. Okay, so covers derivatives. Okay, D-E-R-I. V-A-T-I-V-E-S. T-I-V-E-S. Okay, derivatives. Right, so the word derivative is very, very important. What is the mathematical notation for a derivative? It's this. Do you have a pencil close by? So I don't write on pen. Okay, so I just want to circle this. This is what? A derivative. Why? You've got the f dash x. Okay, f double dash x means double derivative. dy over dx is a derivative. d2y over dx2 is a derivative. So you can just put a note there.
But what are derivatives?
We'll discuss it. Yeah, we'll discuss it just now. Just write down function, and then write down f of x. Okay, so a function would be denoted by f of x. That would be a function. Okay, the functions we've seen a lot. F of x. That's the function. The derivative of the function is denoted by that. So f of x is a function. You can have f dash x, which is the derivative. So that you need to identify. Derivative, or therefore derivative equals f dash x. Okay, I can have a double derivative, then I'll have a double dash derivative. Okay, it's just it's the term. Okay, it's the expression. Okay, we'll look at examples, but this is just theory. Okay, so double dash is a double derivative. Single dash is a single derivative. You can have many different derivatives. Okay, what does the word derivative mean? Well, to derive something means to get something from something else. Does that make sense? Okay, so to derive something. So for example, we can derive fruit juice from fruit. Okay, fruit is the product. Okay, we can take the fruit from the fruit. We can take the fruit juice from the fruit, and then we've got a different product. Okay, so fruit juice is a derivative of fruit. Okay, another thing we could say is jam. Okay, jam. We could take fruit and we could turn it into jam. Right. So a derivative of fruit would be the jam. So derivative just means you're taking something from the function and you're creating something else. Exactly. Okay, so you can have a double derivative, which is a double dash. The other notation is this. D over dx. Okay, or dy over dx. That's also another derivative. So you don't only write a derivative in that notation. Okay, you can put another line. You can say y equals 2x. Y equals 2x. Okay, put a square around that, and next to it just label that function. So y equals 2x is a function. Okay, so the derivative of that function would be this. dy over dx is the notation describing a derivative. Right, so let's write that down. Dy over dx, like that, okay, describes the derivative for that function. It's just fancy notation, right? So mathematicians write down these terms either using f dashed x or dy over dx.
So this describes the derivative for y.
For that function, because that's the function, that's the derivative. That's the function, that's the derivative. Okay, so when I have f of x, I would write f dashed x. When I have y equals 2x, I'd have dy over dx. Dy over dx denotes what? The derivative of the function. Does that make sense?
Yeah.
Okay, so it's just notation. It's like language. Okay, it's vocabulary. Right, so when I talk about a derivative, you'll know I'm talking about f dash x or dy over dx. If I talk about a function is a function. Okay, makes sense. Right, so now we need to understand what does the derivative actually do. Okay, so this is what I want to use for these notes, okay, because these notes help you with the understanding. Okay, so if I have nonlinear functions, what are nonlinear functions? Well, any function with x squared would be nonlinear. Okay, you know if it's positive x squared, the graph is going to do this. If it's negative x squared, the graph is going to do that. Okay, so I've just randomly given you a formula here. Okay, this formula is TR equals 50q minus 2q squared. Is that a nonlinear function? Yes. Okay, I've drawn it. If I draw that graph looks like this. Okay, it's just a graph. It's like any other graph that we've drawn. Okay, you can have graphs like this, like that, straight lines, it doesn't matter. A graph is just a graph. A graph is just a sequence of points. Okay, but what's special about this graph? Well, if you look at, do you know what a tangent is? That we've covered in geometry.
Yeah, I can't remember.
Okay, so when I have a circle and I have a line that touches the circle, that's called a tangent. Okay, so a tangent is just a line that touches a curve. It doesn't have to be a circle. Okay, it was spoken about when we covered circle geometry, but a line is just that, a line. Okay, a line is a special line when it touches a curve. Okay, a curved line. So is this green line curving? Yes. Okay, so can I draw a tangent? Yes, I can draw a tangent here. I can draw a tangent here. I can draw a tangent here. Okay, all of those are tangents. Okay, tangents meaning there are slopes, there are straight lines. Okay, does a straight line have a slope?
Yeah.
Yes. Okay, so these straight lines on the left of this curve, are they sloping up or down? Those three that I drew.
They're sloping up.
They're sloping up. So what would the M be for those lines?
Positive.
Exactly. Okay, so M represents the slope of a straight line, and if I'm looking at a curve, I'm looking at the tangent. Right, what happens as this continues to go up? So if I keep drawing more tangents, eventually the line is going to be doing this. Flat. Okay, what is the gradient of a flat line?
0.
Exactly. Okay, so at some point in time, this goes up, and then it starts to curve. Okay, so at that point, M is 0 because it's flat. Okay, so tangent, flat, and then starting to slope down. Okay, so when the graph starts to slope down, what is M now?
Negative.
Exactly. Okay, so now we've got tangents that do this, and that would be a negative gradient, negative slope. So what do we notice? Slopes for tangents of a curve slope up
0.
and then reach 0 and then start to slope down. Right, so if you're asking about what is the purpose of a derivative gives you a formula that denotes the gradients that touch the line, basically. Okay, so you can use the derivative to find the gradient. Okay, that's what you normally use it for. Right, so every single point in the graph will have a tangent. Okay, that's important to note because that's understanding and then we can apply it. Right, so this is calculus and this is differentiation. Okay, so differentiation follows this formula. This is the formula for the derivative. Okay, that you can write big at the bottom of your page. Okay, these notes I'll send to you. It'll be part of the PDF or PowerPoint, but you need to write this down. You need to recall this. Okay, so this is how we find a derivative. So write down the blue. This is very important. Okay, as it is here, function is y equals that, and then derivative will be that.
What is this function then?
Hey?
What is this function then?
That's just the notation. F of x is just the notation to describe any function. Okay, so I could have had a function f of x equal to x plus 1. That's a function. Okay, so this is the generic function for formats. Okay, any function will have a x and a exponent. Okay, the exponent could be 1. The exponent could be 2, 3, 4. It could be anything. Right, this is the general equation for the function. Does that make sense? Okay, then write that down. Derivative will be dy over dx equals that.
So this is the general equation.
That's the general function. Okay, so how do I get from function to derivative? I need to do this. Okay, so whatever the function is, okay, y equals xn. It's just random. It's just a generic function. Okay, on the next line, write down this. Derivative will be as is, like I've got it here. Okay, write down that second line. Derivative will be dy over dx equals nx to the power n minus 1. Now, derivative will be
over dx, eh?
yes, dy over dx equals an n and then a x and then an exponent n minus 1. Okay, good. Alright, so this is what we do. This is the process of differentiation. Right, what do? You take a function and you get a derivative. Right, so this is the generic equation. What I've got here is the generic. Right, so now we need to practice applying that. Right, so what does this equation say? Well, here's an example. Okay, if I have a function y equals x squared, okay, that's an example. Right, that's the function, that's the expression, okay, the example. Right, if I want a derivative, how is a derivative written? It's written like this, dy over dx. Okay, because I've got a y here and I've got a x there. Right, so what do I do to get the derivative? Well, it's quite simple. What is the exponent of this? What is the exponent of this? 2. So what do I do with the exponent? I write it down. Okay, so I write down a 2. And then I write down x. And then I write down the n minus 1. 2 minus 1. Okay, so what is the derivative of x squared? Well, what is 2 minus 1? 1. So 2x. That's the derivative. And that's what you do. Okay, so all you do is you just take the function, okay, you take that exponent, you write it down in front, and then you minus 1 from the exponent. That's how you get from function to derivative. Okay, that's just one example. Right, so write that example down. Y equals x squared. These are examples, e.g. or e.g.1. We'll do quite a few so you get the hang of it. Example 1, y equals x squared. Put in the second step because the second step is actually the working. That's
so
just
this
the
would be like the graph, like the function.
Yeah, the function y equals x squared. That's the function. Okay, so what am I getting? I'm getting a derivative. How do I get the derivative? I write that down. dy over dx equals 2x, 2 minus 1. Okay, put the working in so you can see that working step. And then the answer is 2x.
So dy over dx
Is the derivative, yeah.
Okay, but dy over dx
Describes
equals
the derivative.
nx minus.
No.
I'm just putting that step in.
Well, that step is this step, yeah.
Yeah, but I'm just going to do that and then...
Okay, that's fine. If you want to, that's okay. And then equals...
So, now you say dy over dx equals 2x, 2 minus 1.
And the answer is 2x. So what is the derivative? 2x. That's the derivative. dy over dx equals 2x. Okay, that's the final answer. Okay, so what did we do? We took a function and we derived a derivative. Right, so here are a few more to try. Okay, these are examples.
So is that all you do?
Yes, that's derivatives. Okay, but obviously they have a purpose. Alright, everything in maths has a purpose, so you use it for something. Right, but right now we just need to know how to find a derivative. That's the important bit. Okay, so here are some more examples. If I gave you another example, here's the example. What is that representing? The function. Okay, so what is the function? Y equals 3x. Okay, if I wanted the derivative is dy over dx. Right? So what is the derivative going to be?
Okay, so
3x
equals
3 minus 1. That's the
so
derivative.
y equals to x3. Then we say the derivative is
dy over dx
over dx
equals...
I'm going to do that other step because it makes sense. Now what is it? nx 1
nx and then to the power n minus 1. Okay, so what is this derivative equal to? What is 3 minus 1?
3x is 3 minus 1 is 2.
Exactly, there's the answer. That's the derivative.
Over dx equals 3x squared. Right. So then that's the answer.
That's the derivative. That's the answer. Okay, so you've got the derivative. Right, here's another one. If I wanted to find the derivative of that, what would that answer be? Okay, so all I'm doing here is just changing the function into something different that I can use. Okay, I can use the derivative for something. Okay, we'll see those things later. Okay, right now we just need to know how to get a derivative
of the function
y equals x squared
cubed.
Cubed, yeah, to the 3.
3x cubed.
No.
Oh, squared, sorry.
Yes. Okay, 3x squared. Okay, good. Alright, so can you find the derivative for this one? Let's again apply the same thing. Y equals x to the 5. So the derivative would be denoted by dy over dx equals. Right, you help me with the next step. How am I going to get the derivative?
Okay. Okay, the next one is y equals x squared. Okay, so dy over dx equals 5
Good.
x 5 minus 1.
Which is 4. Good. Okay, that's another one. Right, and that's what you need to practice doing. So derivatives just follow a specific formula. You write down the exponent and you minus 1 from it. Okay, what happens if the exponent is a fraction? That's possible. Well, let's look at this one together. Let me show you what to do. It's the exact same thing. Okay, so just lots of examples just to get you practicing. Okay.
I may remember this one.
Yeah.
Okay.
Okay, so what happens if I have y equals x to the power a half? Write that one down.
Okay.
Let's look at it. Okay, this is the first time where you've got a exponent with a fraction. So dy over, dy over dx. Yeah.
That's okay.
Okay, a bit too much. Okay. All right, dy over dx equals what? What do? I write down the exponent. Okay, so what is the exponent? A half. Do you agree? So the same thing applies. I write down the exponent, a half. Then I write down the x. And then I write down a half minus 1. See, the exact same formula gets used even though I have an exponent. Doesn't matter. With an exponent with the fraction. The exact same thing applies. You don't change the process. The process stays the same. That's the formula, that's the formula. We just need to apply to different scenarios. Okay, so in this scenario, I write down the exponent, which is a half, and then I write down the exponent, which is a half, minus 1. Okay, so what does that equal? Well, a half. Can I simplify a half minus 1? Yes, minus a half. So x to the minus a half. Right, and that would be the derivative. Right, do you like seeing minus a halves? No. Okay, so minus a half means what? X is in the denominator. So you could rewrite this. See, this is just an algebra step. Okay, you could write this down as this. 1 over 2x to the 1 over 2. Okay, so instead of writing negative exponents, you can write that exponent as a positive exponent, but in the denominator. That's all. Okay, so that's just algebra. Right, but you've done the derivative step already. The derivative step is just this. That's the derivative step. Okay, step 1, step 2, that's it. You can actually stop there if you wanted to. Okay, but I'm just adding more algebra to it, just to show you a bit more. And then I could even simplify that to 2. If I have a half is root x. Okay, the square root gives the exponent a half.
Yeah.
Right.
So it's just like an inverse, eh?
Kind of, yeah, because a negative exponent means inverse, which is correct, John. Okay. Are we good?
Mm-hmm.
Okay. So it doesn't matter what the exponent is, just follow the exact same formula. You write down the exponent and you minus 1 from it. That's it. It's as simple as that. Okay, so let's try another one. There's 2 more examples here. Let's see if you can do these 2. Here I've got y equals x to the minus 1. Right, is this in the correct format? Yes, because the format is this, x to the n. That's the format that you need it in. Okay, if the format isn't in x to the n, I need to change the format. Okay, I can only apply the rule once the actual function is in the correct format. If the function isn't in the right format, there's a problem. Okay. So now I've got x to the minus 1. dy over dx is going to equal what? You tell me.
100 now?
Sure, no problem. Okay.
Okay. Okay, so x to the minus 1, so...
Yeah, y equals x to the minus 1. Yeah, so dy over dx, what's the rule? Write down the exponent, right? Which is minus 1.
Minus 1.
Then
X.
write down the x.
Minus 1.
Exactly. See, easy, hey? So what does that give you? We don't write minus 1, so you just write that. Okay, you can drop the 1 and then minus 2. Okay, do we like negative exponents? No. So you could write this as minus 1 over x squared. Okay, it's the same thing. That's just an algebra step. Okay, that's the derivative. You could stop there if you wanted to. Right, last one. dy over dx is what? Let's check. Right, what you're doing is calculus. It's differentiation. It's one process to get something that we can use. Okay, so all these derivatives that we've got here can be used for something. Okay, that we'll only see later on. Yeah, y equals x to the minus 3. So that's the function. How do I get the derivative? Apply the same process. What do I do?
Okay, so it's minus 3.
Correct. Correct.
Minus 3 minus 1.
Exactly. Easy, hey? Minus 3, x to the minus 4. Do you like negative exponents? No, so you could write this down as this. That's just an algebra step. Alright, happy with this? Okay, it's really simple, it's just practice now. Okay, so that's the process for looking at derivatives. Right, there's a few more here. We don't have to look at all of them, but there's something that I want you to identify, which is this, the constant. Okay, so what happens if I have a number in front of the exponent? Okay, so we'll do two of these. We'll actually do them all. They're actually quite short, but you'll see it gets quicker just now. Okay, so this one, dy over dx. Okay, I'll do the first one with you because it's different. Okay, so when I have a constant in front of the x, okay, what do? I leave the constant, but I just times the number into it. Okay, so if I have 3 as the exponent, what is 3 times 5? 15. X to the 3 minus 2. 15 x minus 1, which is 2. Okay, it's the exact same thing. Minus 1, 2. There's the derivative. Right, so derivative of this is that. Okay, and when you get more comfortable with this, you should be able to go from here to there. Okay, you shouldn't need to have to write this down. Okay, it's fine now because it's new, but I mean, like, I wouldn't write that step down. I would just go from there to there, that's it. Okay, 3 times 5, 15. 3 minus 1, 2, the end. Okay, but if you want to put the middle, you can. Okay. Alright, so that's the one. Okay, the reason why I've given you some different variables here is to show the different notation. Okay, so let's change the notation. Now we're looking at S's and T's, so that one over here. Okay, so how do I get from here to the derivative? Well, quite easily. What is the derivative? If I've got s and I've got t, the notation will change. Okay, you don't have y's and x's. So the notation here would be ds over dt. That would be the notation.
Okay, I'm just finishing this one. Okay.
Okay, so they can give you different variables. They don't have to give you y's and x's.
Yeah.
It could have been something different, which it is in this case. Okay, so if I give you s's and t's, do I apply the same process? Yes, exactly the same process. Right, but now instead of dy, it's going to be ds. Instead of dx, it's going to be dt. Right, then what do? I just times the exponent to the number. What's 5 times 2? 10. T, what's 5 minus 1? 4. There's the derivative. There's the answer.
Okay, so yeah, we've got y, s equals 2t. S equals 2 to the 5. So then it would be
ds over dt is the derivative. Okay, I haven't put the middle step in. You can if you want to, but I don't think it's necessary. It should be getting easier and easier with more examples. Okay, so you write down the exponent times the number, you write down the exponent minus 1, and that's it.
okay, cool.
Okay. Alright, let's just quickly do the last three. They're quite simple. I'm going to write this out. Okay, so this one would be dx over dy. Okay, slightly different. The only reason why is because the notation is giving x here. Okay, so what would the derivative be? What's a half times 10? 5. Y to the half minus 1, which is 5 to the y minus a half. Okay, I'm going to leave it as is. That's the derivative. There's no need to take it further. You can leave it as is. Alright, so what happens if there's a constant? Constant being a number that's going to be added to the actual expression. Well, when you have something like this, derivatives of constants are 0. Okay, so when I have any number without an x, the derivative is 0. There is no derivative for it. So when you have an expression like this, y equals 10 plus x to the minus 5, you just drop off all the constants. So dy over dx is equal to, what's minus 5 times 1? Minus 5. X minus 5 minus 1, minus 6, and that's the derivative. Okay, so constants fall away.
Okay, so I'm going to say they fall away.
It doesn't matter what the constant is. The constant can be 1,000,000, it'll still fall away. As long as it's a constant, okay, i.e. a number without a variable. Okay, so that 10 didn't have an x. That 32 doesn't have an x. So you just drop them. Okay, you drop the constants.
How did you get? Okay. So you just drop it.
Drop the constant.
Okay, so I'm gonna do this for you. I think it's me. And x and minus 1.
Oh, so the n there is minus 5. X. Minus 5 minus 1. Exactly, which lands up with that. You can leave it as is. Okay. Right, so the last one, you find the derivative for this one. What would dy over dx be for this one at the end here? Differentiation, I see, is chapter 6 in the textbook. Okay, what's the last one going to be?
Still the same.
Okay. Minus times a minus is a?
That's right. Minus 6. Minus 6x.
No, minus 6. Minus 6 times minus 1 is what? There's a minus there's a minus here next to the x. Minus 6 times minus 1?
6.
Plus 6. Okay. X minus 6 minus 1, which is 6x to the minus 7. Okay, negative times a negative is a positive. Right, and that's it. That's differentiation. Okay, the last bit here is just this whole idea of second and third derivatives. You can be asked to find higher order derivatives. Right, so I'm using this as an example just to show you a derivative of a derivative. Okay, remember that dashed, the double dashed? See, it's a notation. This is single derivative. That's double derivative. That's third derivative. Okay, if this was a function, if this was f of x, then you would have f dashed x, then you would have f double dash x, and then you'll have f triple dashed x. Okay, right, so let's find the derivative. First derivative of this equation. Well, I've got 3 terms to derive. Right, so the first term, what's 5 times 120? Could you work it out? I think it's 600, hey? No.
Yeah.
Yes. Yeah.
Yeah, 600.
Okay, so 600. Q. What's 5 minus 1? 4. Okay, there's the first derivative. Then the second one, what's 2 times minus 100? Minus 200. Q. What's 2 minus 1? 1. So that stays there. What's the derivative of 40? It doesn't have a derivative. It's 0. Okay, there's no derivative. There's the first derivative. Right, is it possible to get a second derivative? Yes. What's 4 times 600? 2,400. Q. What's 4 minus 1? 3. Okay, what happens when I have a 1 here? Well, what's 1 times this? Minus 200. Okay, then what do I have here? Well, do you agree the derivative here would have been Q 1 minus 1? What is 1 minus 1?
0.
0. What is anything to the power 0?
0.
No.
1.
Yes. Okay, any exponent to the power 0. So I can have 1 to the power 0, x to the power 0, 10 to the power 0. If you type in that into your calculator, put in 10 to the power 0, you get 1.
Yeah.
Okay, so anything to the power 0 is 1. So we don't write down expressions with the power 0. Okay, so all of that can go. All you do is write that down. Right, because it's 1. Right? So it'll be minus 200. Okay, there's the derivative. Right, can I get a third derivative? Yes, I can. Right, what's 3 times 2,400? 7,200. Q. What is 3 minus 1? 2. What is the derivative of minus 200? There is no derivative of minus 200. You drop it. Right, there's the third derivative. Okay, so first derivative, second derivative, third derivative. You can find derivatives of derivatives. Is that okay? Alright, so let's just wrap out these things. There. Okay, and that's the last bit that we needed to look at in terms of the derivatives. That's my last slide. Okay, and then we can summarize more of what we need to look at here in this section. Okay, but that's the basics. Okay, once you understand the basics, then it's easy to do different calculations.
Okay, so first derivative.
Yeah, first derivative. So dp over dq would be the first derivative. And you can just write down that answer. First derivative is dp over dq. Okay, because I've got p here and I've got q there. That's why. It could have been y and x. Doesn't matter.
So why didn't we do a derivative for this again? Because for the 40?
Because you drop the constants. Right?
Yeah, I'm just doing notes.
Sure. Yeah, so it's just derivatives of derivatives. Just remember that anything to the power of 0 is always 1. Okay, and that's the reason why you just drop that variable, okay, when you go from minus 200q to minus 200. Okay, there you go. Perfect.
So obviously this one had no exponents and stuff. So
well, here we had what? We had minus 200q, right? So the derivative of that is just minus 200. Right, you drop the q. Okay, the reason why you drop the q is because q1 minus 1 is q0, and q0 is 1. Okay, makes sense. Right, then there are lots of examples here in the work program. See, they've given you a few examples here. Okay, the only thing that I want to mention here is you can put a note here. Just write down additional considerations. Number 1, simplify first before applying the derivative rule. Okay, that's very important. So you have to simplify first before you apply the rule. Okay, remember that rule that we had, that n, the nx to the n minus 1? That you can only apply once you've got a simple expression. Okay, so you must always simplify. Yeah, so I'm going to just use one of these as an example just to show you what I mean. Okay, there's a big one. See? E, the last one. Okay, so just you can put one example there just to show this. We're just going to need 2 lines there, those 2 lines. Okay, this, so this, just write down that, that's the question, that's the example. Okay, that's the next step, and then that's the answer. Okay, that just shows the working, which you don't have to do because you've been doing it already. Okay, alright, so this expression is y equals 3x to the 7 over x over 4, 3x to the 7 minus 4x squared all over x to the power 5. Okay, that's what I mean by simplify. Right, so you must simplify first, then you just apply the normal rule. The rule never changes. Okay, the differentiation is the differentiation. The only thing that they can do to make this more difficult is to ask you to simplify first. Right, so now looking at this, that looks difficult. I can't differentiate this as is. I need to simplify first, then I can differentiate. Okay, and that's the trick. Right, so whenever you have a question, just remember that. Simplify first before you apply the rule. There's one example. That's the best example there because you've got a massive one. Okay, numerator and denominator. Yeah, just write down the question and then you can do the steps. Okay, and that covers the differentiation. That's the basics.